Dear viewers, welcome to the UGC lecture series in Biophysics. Today we are going to learn Fourier methods in X-ray crystallography. Fourier methods or Fourier techniques is a discipline in mathematics, and X-ray crystallography is one of the disciplines of biophysics. When you talk about biomolecules, it is also called biocrystallography. In this topic Fourier series, we are going to first learn about Fourier transform. What do you mean by Fourier transform, or the exact definition of Fourier transform, and the reciprocal lattice and the Fourier series connection, and how is the structure can be obtained from Fourier synthesis, and what do you mean by convolution of two structures, or in other words convolution theorem, and what are the various types of Fourier series, and the importance of phase angles in the Fourier synthesis. Coming to the last two topics, seminal amount of work has been done by Professor G. N. Ramachandran and his colleagues in the Center of Advanced Study in Crystallography and Biophysics during 1952 to 1968. Let us first see or introduce what we mean by Fourier transformation. Fourier transformation is used to project the interrelation between the scattering phenomena and the structure of the scattering material. Already you know what do you mean by X-ray diffraction in X-ray crystallography. You know, the smallest unit is a unit cell in which molecules made up of atoms lie. When you splice the unit cell in the three directions, we get thousands of planes, and these atoms containing planes, when they meet the X-rays falling on them, the electrons in these atoms interact with the X-rays. That is known as scattering, or to be in particular diffraction. So what we measure from experiment is the diffraction intensities. So for which Bragg's has given a law, along a particular direction, diffraction is maximum, given by Bragg's law, 2d sin theta equals n lambda. So this phenomenon of diffraction being produced by a crystal is discovered by the scientist, German scientist Max von Laue. So all these three people received Nobel Prize. Of course, the discoverer of X-rays, Röntgen, also received the Nobel Prize. So this is a history. When you talk about the Fourier transformation, it gives a relation between the electron density contained in the atoms of the molecule and whatever you get as output is the diffraction phenomena, which are the intensities of Bragg reflection or the structure factor amplitudes. So one is the real space, other is the reciprocal space. We are going to discuss in detail about all these things. This Fourier transformation has reached its great impact on science by its usage in explaining particularly the diffraction materials. And there is a famous book written by Professor G. N. Ramachandran and his second scholar, Professor R. Srinivasan. This book has been published by Wiley, and the title is Fourier Methods in Crystallography. Whatever we are going to talk about in this presentation, it mainly comes from that book. Let us define what we mean by Fourier transform. All of us know that atoms are surrounded by electrons. Only wherever atoms are found, electron density will be distributed. If rho of r denotes the electron density distribution in a piece of matter, then the scattered X-ray wave after diffraction is in direction defined by the scattering vector r star given by equation 1. So we write the structure factor in the reciprocal space r star, f of r star, as an integral expression involving rho of r, which is called the Fourier transformation of rho of r. This modulus of structure factor is measured by considering the scattering amplitude of single free electron under the same conditions to be equal to unity. The Fourier transform f of r star of rho of r, the electron density, is obtained in equation 1 by multiplying the electron density rho of r by the kernel exponent e power 2 pi I r dot r star and integrating over the entire volume in the space r in which rho of r is defined. This is the real space. So we write f of r star as t. T means Fourier transform of. So f of r star equals t of rho of r. Here t denotes the multiplication by the kernel exponential 2 pi I r star dot r and also integration over the appropriate volume of the space. So this is equation 2. Now rho of r can also be written as an inverse relation, namely rho of r equals integral f of r star e power minus 2 pi I r dot r star dv r star as given by equation 3. Only difference between the previous equation and this is that the kernel sign is minus. Now rho of r, which was in the integral, now it becomes f of r star, that's all. So we can also write an equivalent expression, f of r equals integral rho of r exponential 2 pi I r star dot r dvr. Then we see rho of r equals inverse transformation of f of r star. So when you write T inverse, it means inverse Fourier transform. The spaces of r and r star have the reciprocal relationship. And the simple example we want to see, A, B, C are the unit cell vectors, cell constants. In the reciprocal space, they are A star, B star, C star. For a simple system like cubic, A star equals to 1 by A, B star equals to 1 by B, C star equals to 1 by C. So this is a simple relationship. According to the crystal system, we have different relationships. In diffraction phenomena, it is conventional to call the spaces of R as direct or real space corresponding to the space of the scattered material. But the space of R star is called as reciprocal space, and this corresponds to the space of the observed diffraction phenomena. Now what does R dot R star determine? This is equal to R star cos theta. This is the multiplication factor because there's a dot product. R dot R star is equal to multiplication of R and R star and a factor cos theta, where theta is the angle between the direction of R and R star. Now if we denote R of j, where j running to n atoms in the unit cell, to represent the vector specifying the position of n atoms with respect to the arbitrarily chosen origin. If f of j of R star is the Fourier transform of the atom j referred to its center as origin, then the Fourier transform of the atom at Rj atomic site is fj of R star multiplied by the kernel e power 2 pi I R star dot Rj. In other words, we get equation 5 as f of R star equals summation j equal to 1 to n fj R star exponential 2 pi I R star dot Rj. Now we will see the relation between the reciprocal space and the Fourier series. Fourier transform of a crystal has appreciable values only for certain directions of scattering specified by the diffraction vector R star being equal to the vector H, which is equal to HA star plus KB star plus LC star, where the small h, k, l are all integers to define a Bragg plane. So these are called Miller indices, which can be both positive and negative and also 0. The termini of the vectors H vector for all the values of h, k, l form an infinite lattice with unit translation in the reciprocal space as A star, B star, C star. We will be covering more about reciprocal space later, because we are going to learn about Ewald sphere construction, using which Bragg's law can be easily visualized. Whenever a crystal rotates, the reciprocal lattice also rotates. Whenever a reciprocal lattice cuts the Ewald sphere, that point undergoes Bragg's law. So this is the equivalent way of expressing the Bragg's law. In the reciprocal space of crystal lattice, the Fourier transform is non-zero only at points specified by the reciprocal lattice vector H. The intensities of the diffraction wave at these points are proportional to mod fh square, because as I told you, the expression itself structure factor, as you can see from either 6 or 7, you have a quantity I, which is called imaginary, because I square equal to minus 1, I is square root of minus 1, which cannot be done, so which is called imaginary. And because of this nature, equation 6 and 7, fh on the left hand side is a complex quantity. Any complex quantity has an amplitude and a phase. Now that's what we mean by measured intensity is nothing but proportional to mod fh square. And here f of R star is already defined by equation 5. You have seen in regular crystal diffraction only the function mod fh square has to be considered, which is nothing but your intensity of Bragg representing HKL you are measuring from single crystal diffraction experiment. Now we can write equation 6 and 7 in different ways, relating structure factor and atomic scattering factor in terms of the position vectors Rj. If you look at equation 6, Fj represents atomic scattering factor of atom J. J can be carbon, hydrogen, nitrogen, oxygen or hydrogen. That can be situated at a position called Rj. Ultimately, I want these three positions Xj, Yj, Zj, which are meant by the vector Rj. Now, every atom J has a contribution to diffraction. So, like that, capital N atoms are there in the unit cell. If so, what will be the contribution coming out of the contents of the unit cell? That is defined by left hand side as either f of capital H or f of HKL. So don't consider the product HKL. This is notation we mean in crystallography, f of HKL. Such a factor corresponding to HKL can be defined as a summation over all atoms running from J equal to 1 to N, the product of atomic scattering factor Fj and the exponent containing e power 2 pi I Hxj plus Kyj plus Lzj. Ultimately, towards the end of the diffraction experiment, one is interested to know the three positions Xj, Yj, Zj of individual atom J, that is known as three-dimensional structure determination. In terms of the continuous electron density rho of R, if V is the volume of the unit cell, which can be calculated if you know the lattice parameters A, B, C, alpha, beta, gamma, equation 6 can also be written as an integral expression f of h equals integral over volume B rho of R e power 2 pi I h dot R dVr, where B denotes the integration over the volume B of the unit cell. So, equation 8 is the Fourier transform in integral form for defining such a factor f of h of a reflection. The inverse form of equation x is also possible. It has the form of Fourier series rho of R equals 1 by V summation over h. When it means summation over h means both HKL indices, a triple summation as given by 10. So rho of R in 9 equals 1 by V summation over h f of h e power 2 pi I minus 2 pi I h dot R. This f of h, occurring in the right hand side in the summation of equation 9 has two parts, because as earlier you have seen, f of h is a complex quantity. So any complex quantity will have an amplitude, say as given in 10 mod f HKL, and a phase phi HKL given in 10. So f of h equals mod f HKL e power I phi HKL. This is from trigonometric experience. Any complex number can be written as a product of two terms. One is amplitude, other is e power I times phase, which can be represented in Argand diagram. Now if we look at equation 10, I define rho of x comma y comma z, which I denoted as rho of x y z. It's not a product of x y z. Electron density at a point x comma y comma z is represented as rho of x y z, which is nothing but 1 over V volume of unit cell, triple summation over the Miller indices HKL running from minus infinity to infinity mod HKL, which is available from the square root of the measured intensity experimental value square root of I HKL, then e power I phi HKL multiplied by the exponent e power minus 2 pi I Hx plus Ky plus Lz. This is important equation, again called Fourier synthesis in X-ray crystallography. If you look at the right hand side, the experiment gives you only the amplitude mod of HKL on the Bragg from Bragg intensities. Phi HKL on the phase of the Bragg reflection from experiment is unknown. Unless you know phi HKL, you cannot calculate the right hand side. Unless you know the right hand side, you cannot find what are all the values of the electron density at these thousands of points in the unit cell, from which atomic sites are those which will have maximum value of the electron density. So this is known as phase problem, the non-availability of phases which are required along with the experimental magnitudes to calculate electron densities to determine the atomic sites. So equation 10 is very, very important. It's called as Fourier synthesis. That is the relation between the mathematics and biophysics. Equation 9 and 10 denote not only the electron density distribution in the unit cell, but also an identical distribution in every unit cell of the crystal. Then if you look at the crystal, as I told you from the beginning of the lectures, in crystallography for diffraction quality, we need a single crystal of dimension 0.2 millimeter in length, 0.2 millimeter in breadth, and 0.2 millimeter in thickness. So This small 0.2 millimeter cube volume of the crystal will contain millions of unit cells. That's why I'm talking every unit cell of the crystal has identical distribution. So we have seen now Fourier series representation of electron density. In a crystal, the exact inverse of this equation 10 we have seen is the explicit form f of hk equals integration of electron density at a point x comma y comma z e power 2 pi I hx plus ky plus Lz dV of r. Here the exponent has the positive sign. That's all. V denotes the volume of the unit cell. Now, how to obtain the structure from Fourier synthesis? So that already is seen, because we have to know both amplitude modification and phase of the phi h. A Fourier synthesis with the coefficient f of h, the complex quantity, which can be rewritten as mod f h e power I phi h, leads to the structure in direct space. Structure means I get positions of atoms, j from 1 to n atom, xj, yj, zj, of which the structure factors or the Fourier transform correspond to lattice point h. Thus, if the structure contained within the unit cell consists of atoms of scattering factors little fj at position rj, this could be recovered in the Fourier synthesis. Ideally, if all the Fourier coefficients with h, k and l up to infinity are included. But practically speaking, beyond certain angle of incidence, we don't have any diffraction waves coming out of the crystal, which means that beyond certain HKLs, even though theoretically speaking they can go up to minus infinity, beyond certain values, we don't have any intensities coming out. So intensity will be 0 or such effect amplitude will be 0. So there is no meaning in including all these things in the summation of the Fourier synthesis. So whatever we have given, Fourier synthesis equation, that is known as F synthesis, F denoting Fourier. Symbolically, little fj, rj, where j runs to 1 to n atom the unit cell, leads to f of h or structure factor. Or little f nj, the n atoms, j running from 1 to n, at positions r nj, leads to f n of h, the total contribution to the diffraction from n atoms in the unit cell. So we can denote it as f1 of h leads to fnj, or nj. Thus, a synthesis with F1H as coefficient will yield a structure with atom of strength of Fnj at Rnj. If F dagger, so that maybe symbol above F denote dagger. Dagger means complex conjugate. If there is a exponent positive in f of h, F dagger h will become negative exponent. That's all. If F dagger h or the complex conjugate of f of h is defined, then we define this complex conjugate of f of h, namely f dagger h as mod f h e power minus I phi h. Previously, f of h was mod f h e power I phi h. Now, f dagger h is, that exponent becomes, now it's a plus I becomes minus I. So now you say fj, minus rj, the inverse of the structure, leads to f dagger h. If a Fourier synthesis f1 of h leads to a structure Fnj with coordinates plus Rnj, then the synthesis F dagger H will lead to a structure with Fnj minus Rnj. This synthesis of F dagger H is known as conjugate synthesis to Fh, and structure Fj, minus Rj is called the inverse structure, because position Rj is coming as minus Rj. This is obtained from the original structure by inversion of the origin. Now we come to an important topic called convolution of two structures. This convolution theorem has been meticulously used by Professor G. Ramachandran, the founder of the Center of Advanced Studies in Crystallography and Biophysics in University of Madras in the year 1952. He was there from 1952 to 1968, and all his seminal discoveries in crystallography and biophysics came only from that lab. Now, he has used the convolution theorem to get the 3D imaging from the two-dimensional plot, two-dimensional sheets. So that's called convolution of two planes to get the third direction. So here we will see mainly the theorem. Later we will see what was the GNR contribution towards this convolution theorem, getting the 3D images from 2D planes. If f of r, little f of r and little g of r denote two structures in 3 dimensions, then how you define the convolution q of r of these structures? Q of r is integral. You place the function f of r, put a symbol star, multiply by g of r. What do you mean by convolution? Convolution, in one of these r, it is shifted r minus r dash, and the other g position is replaced as r prime. So, when you define the convolution of two functions f of r and g of r symbolically as q of r equals integral f of r star g of r, that's equivalent to f of r minus r prime g of r prime integrated over the volume dv r prime, which can also be written as, you can shift in g also instead of f, which can also be written as equation 13 integral f of r prime g of r minus r prime dv r prime. Now, if every these functions f of r, g of r and the convoluted function q of r have the Fourier transform respectively as q of r star, f of r star and g of r star, then we say q of r star, that is the Fourier transform of q of r, which is the convolution of two functions, is equal to f of r star multiplied by g of r star. F of r star is nothing but Fourier transform of little f of r. G of r star is nothing but Fourier transform of little g of r. So now we can state the convolution theorem as Fourier transform of the convolution of two functions is equal to the product of their individual Fourier transforms. That is what 14 says. Patterson, he has contributed a lot in the field of X-ray crystallography. In the years 1935, 1949, he had shown that the Fourier synthesis performed with intensities I of the X-ray reflections as coefficients contain high values corresponding to the interatomic vectors between the atoms in the structure. So now you must understand the difference between a Fourier synthesis or F synthesis and a Patterson. Fourier synthesis directly will give you the atomic positions Rj or Xj, Yj, Zj of atom J running from 1 to n, whereas the Patterson gives you only the interatomic vectors Rj, Rj prime or Ri, Rj. But the input to the Fourier synthesis should be both amplitude of Bragg reflection and phases of Bragg reflection, whereas Patterson does not require the phase of the Bragg reflection, mere intensities are enough. So that is the advantage of Patterson. Phase problem is not there, but it gives the only interatomic vectors. We have to find the individual atomic positions later. That's okay. Patterson has a lot of use in the field of macromolecular crystallography, which we will be seeing when we talk about the topic. Now, when we talk about intensity of Bragg reflection, which is nothing but f of h multiplied by f dagger h, which means the product of such a factor and its complex conjugate. We can also say that the Patterson is a convolution of a structure f of h consisting of the atoms in the unit cell with this inverse structure f dagger h. We already know that if we define a structure f as containing f of nj at position vector r of nj, then the inverse structure f dagger h will contain peaks of strength fnj not at position rnj but at inverted position minus rnj. Thus, the Patterson synthesis should contain peaks of strength fni, fnj, product of the individual scattering factors at positions rni minus rnj. That's called interatomic vectors. The Patterson uses mod f square or f multiplied by f dagger as coefficient for its Fourier synthesis. The synthesis uses f square as f dot f as coefficient, and this is known as a squared structure. The Ramachandran and his student Raman in the year 1959 published a seminal paper titled Synthesis of the Deconvolution of the Patterson Function. For the first time, modular structure was described by them. It is a Fourier synthesis obtained by feeding it in separately the modulus part mod fn. It has been elegantly proved by them that The principal peaks in the modulus synthesis are exactly at the same positions as in the Patterson synthesis, and the ratio of the non-origin to the origin peaks in the modulus synthesis is reduced to half compared with the same value in the Patterson. Especially, however, the modulus synthesis has the same nature as the Patterson synthesis. If one compares the synthesis using mod f, mod f square and mod f power 4 as coefficients, the peaks appear at same points only, except that the strength of the peak differs. For a 5-atom model, the average of the ratio of non-origin peaks to the origin peaks in the three syntheses are 0.14, 0.23 and 0.4, agreeing broadly with the theoretical expectation that these should be in the ratio 1:2:4. So dear viewers, let us stop at this stage first and recollect what you have learned now. I have given an introduction about the Fourier synthesis, what is its role in X-ray crystallography, what do you mean by inverted system, what do you mean by real and reciprocal lattice vector, what do you mean by a Patterson synthesis, and how many syntheses are possible, which have been worked out by Professor G. N. Ramachandran and his colleagues. We will continue this topic next time. Thank you.